Hello everyone, so this is the second part of the 555 timer video. I cut the first video to 5 minutes to make it short. At the end of it we tested the circuit, but I never explained where that circuit comes from, and I did not really detail what is the advantage of this board. So this board gives access to the various components of the 555 timer. This is a very interesting board because we can actually test the internal components of the 555 timer. We can test voltages between pins that are normally not accessible when you use an integrated circuit of the 555 timer. So if you haven't seen it, please go see the first video. This is the second part, and we're going to look at the circuit. So before we do anything else, we need to look at the 555 timer one more time. So we're going to connect pin 1, 2, 3, 4, and we're going to ignore the fifth pin. So in fact, what I'm going to do is I'm going to draw it. I didn't draw it because we're not going to use it today. So what we're going to do is we're going to use the 555 timer in astable mode. The 555 timer has three possible modes, and we're going to use the most common one, which is the astable mode. We're going to connect VCC to 9 volts. So that's going to be our 9-volt line. We're actually going to connect the reset pin to VCC. We're going to actually connect a LED to the output. But the output, if we put 9 volt here, the output would actually be a 9-volt output. And most LEDs, they use between 2.5 and 3 volts, something like that. So what we're going to do, the first thing we're going to do outside of this, outside of the output, is we're going to put a resistor. So here I'm putting a resistor. So that's going to be our first resistor. And we want something on. So on this side we have 9 volts, but we want something less than 3 volts on this side. So in order to have less than 3 volts, I'm going to use a 1K ohm resistor. Right, so it's going to be a 1K ohm resistor on that side. And then, of course, the LED. So that's our circuit. We're going to make a LED blink, right? And it's going to be a light emitting diode. So, okay, here we go. That's light emitting, I guess. And okay, and it's connected to ground. All right, that's good. And of course it's ground, so I don't know. Here we go. So now the 555 timer has also 3 resistors. So that's those guys here. So 1, 2, 3 resistors. And they happen to be 5K resistors. And I looked at the story of the 555 timer before doing this video, but contrary to what I thought, the fact that I have 5, 5, and 5K resistor has nothing to do with the name. The 555 timer apparently was not the reason. Nobody can actually agree on the reason why the 555 timer is called 555 timer. If you have any idea about this, I'm kind of curious. All right. Okay, so it's good. We're going to now we're going to connect the discharge, the threshold, and the trigger. Okay. We're actually going to directly connect the threshold and the trigger together. So they're going to be like that. Between the threshold and the discharge, I'm going to put a resistor here. And I'm going to put another one right there between the discharge and the 9-volt line. Alright. So okay. So we're going to connect this charge to a resistor. So it's gonna be a 100k ohm resistor. So this was at 1k, this is 100k, so it's 100 times more. And another 1k resistor here. Alright, so and the last component that we're going to use is gonna be a capacitor. So yeah, we have a capacitor. So obviously the 9 volt is coming on that side. So in fact the positive side of the capacitor is gonna be this guy, and that's gonna be the negative side. The negative side is of course going to be connected to ground. So that's the circuit that we're going to use today. And the whole point of actually building this card is that once you've built this card, you can actually look at the voltages along the way. So you do not have access to the internals normally on a 555 timer, right? It's an integrated circuit, right? It's a IC, so I should call it IC 555 timer, integrated circuit. Well, ours is disintegrated circuit, right? We've actually, blown it up. It became a big thing, right? So in fact, it's very educational. This 555 timer board from Adafruit. I highly recommend it. First of all, because it works, as we saw in the first video, but also because it's for me it was a revelation, because I finally, I think, kind of understand how it works inside. I'd never really looked into the 555 timer schematics, and actually a lot of them are actually wrong. This is a graph that came from Wikipedia, but I actually had to change some of it. I mean, the reset is common here on this side. This wire is actually one wire only, and it was there was several things that were wrong on that chart, on that circuit. So anyway, and there's no legend, bizarrely. I mean, it's not right, but anyway. Okay, so now we have our capacitor. I'm digressing. Right, so there's a 1 microfarad recommended, the recommended circuit. I think that my circuit is easier to understand than the little circuit that came with the board. So the board recommends doing this, but I think it's convoluted. It was like, the first time I looked at it, it was like, okay, I don't recognize the astable circuit. And the astable circuit is everywhere. I mean, this is something that has to be known. So here we go. So this is what it looks like, right? So now we've connected the circuit properly. So right there, as we can see that pin 2 is connected by the red wire to pin 6. The 1K resistor coming out of pin 3 is going to the LED, and the LED is connected to the negative ground rail through that gray wire, and I connected both the top and bottom rails with the negative rails with the gray wire and the positive rails with that red wire on the right. Pin 4 has been connected to the reset. The reset pin has been connected to the positive rail. The yellow wire has been connected to ground, and that's the pin 1. On the other side, pin 8 is connected to plus 9 volt, right, through the rail, and the two 100K resistors are put sideways and are connecting pin 6 to pin 7 and pin 7 to pin 8. All right. And that's about it. That's the whole circuit. So now, if we turn on this circuit by putting a battery between a 9-volt battery between the positive and negative rails, the LED is blinking, and it's blinking quite fast. It actually depends on the values of the 100K of the two 100K resistor as well as the capacitor. So the size of the capacitor, the size of the resistor determines the speed of the light. And so once we remove the 555 timer, we can replace it by our giant 555 timer, and we reconnect the battery, and that's as simple as that. We reconnect the battery, and it's exactly the same circuit. The only thing I've changed is that I've connected each one of the pins of the giant 555 timer to the breadboard, and the only thing that is left to do is actually to turn on the power from the battery. So the 9-volt battery is actually going to turn on the light by the virtue of current flowing through our giant board, and we get exactly the same speed, and we get exactly the same effect with same voltages. So our big board is replacing that tiny integrated circuit just perfectly. Just as mentioned earlier, pin 5 is not used, and so I did not connect pin 5. And every other pin, 1, 2, 3, 4, 6, 7, 8 have been connected. Anyway, so alright, so if we have those 5K resistors in the middle of that ground, which obviously is 0 volt, right? 0 volt on this side. So if we have 0 volt here and VCC 9 volt at the top, well, we have 3 resistors of equal size. So at each junction, we're gonna have one third of the voltage, right? So at this place we're gonna have 3 volts, and right there we're gonna have 6 volts. Okay, so what are those? So those are actually comparators. So I'm gonna call it comparator 1. I don't know what their name is really. So I'm gonna call it comparator 2 and comparator 1. Alright, so this is actually what we built, right? When we built when we soldered all those components, we actually built one comparator, another comparator, the SR latch, which is sometimes called flip-flop, but it looks like a SR latch to me. Alright, and the output, okay, and we have that discharge with this transistor. Okay, so we have one more thing. We have that transistor for discharge. Okay. Well. Okay. So we are turning on the circuit. Okay. So if we turn on the circuit, I need another color. It's not gonna work. Okay. So we're turning on the circuit. We're at 0, right? We're starting from 0 volt. There's gonna be time here. So I'm gonna call it time. Okay, and that's the voltage, right? So voltage. Right. So we have time on the x-axis, and then we have the voltage on the y-axis. Okay, we're starting at 0, time 0, and then voltage 0. Okay. So okay. So all along the way, okay, we have 0, right? So on this side, we're still at 0, right? We have 0 volt. So okay. So we have 0 volt on that trigger, right? So that triggers at 0 volt, and that's a comparator. Okay, so if the trigger is at 0, we're comparing to 3 volt, right? So we're below. So okay, so this is plus, and this is minus on the comparator. Actually, the other comparator is the opposite. This is the plus, and that's the minus. All right. So we're below, right? We're below. We are. So okay, so it's true, right? It's so okay. So 0 is definitely below 3. Okay. So we're on. Okay, so good. Okay, so here we go to the set of that SR latch, right? So SR stands for set and reset. Okay, so that's set, and this guy is reset. Okay, Q is the output. Okay, and Q bar here is non-Q. So that's the opposite of Q. It's actually the that's the non-Q. It's an inverted output. So we have the output, and inside of the 555 timer, they also have an inverted output. So output, inverted output. Okay. All right. So we set. Okay. So we're on. We set. Okay. So now the SR latch is set. It doesn't matter anymore what that value becomes here, what it compares to. Even if the voltage goes above 3, it's not gonna change it anymore. It's been set. Okay, so set means, okay, turn on Q. Okay, so turn on Q, it means send 9 volt. Okay, so 9 volt goes to this resistor, and it becomes a bit less than 3, and boom, our LED is on at that point. All right, so LED is on, and then we're actually outputting 9 volt. So actually, I need my green pen. Okay, we're outputting 9 volt. Okay, so this is 9 volt. It's the max we'll ever output. All right, we're outputting 9 volt. So we're outputting it. Okay. All right, but look at what happens. Okay, we've turned on the power, right? So now the electricity can actually flow, right? The electrons are gonna be able to flow in that circuit. Okay, so electricity is flowing, goes through the first resistor. Well, nothing happens on the discharge thing. We can forget about that, because in fact we have non-Q here, so we've set it on Q here, so we have plus 9 here, but right now non-Q is at 0, right? So okay, so we're at 9 volt here. Sorry, at 0 volt on the non-Q. Okay, so nothing happens, doesn't go to ground. I mean, again, so this transistor is locked, there's nothing discharging. Okay, so it cannot go there anywhere. Okay, so it keeps flowing here, and okay, so it charges the capacitor. All right, I need to write capacitor. All right, because all right. Okay, so it's charging the capacitor, and it's charging, and at some point it reaches 3 volt. Actually, it reaches, let's say, 3.1 volt. So it's gonna be 6 volt and 3 volt, 6 volt on this axis. Okay, so it reached 3 volt. It's gonna keep going to 6 volts. Right. So, but first it goes through 3 point something. All right, 3 point something. So now we on the trigger we have 3 volts. Well, the trigger being lower than that reference voltage is false. So here we were on, but now we become off. Okay, so now we're off on that side, but we've already set, so nothing happens. Now on this side, well, okay, so this whole wire is so from here down to here we are at 3.1, right? So the threshold is also at 3. So is plus? I mean, is 3 greater than 6? No, it's not. Okay, so that reset is also off. So this is off and this is off. So both of them are off. Okay, so but we've already set. So Q is still on, right? That's how SR latch works, right? Okay, perfect. So nothing. Okay, so on this side nothing happens. So the light is still on, all the way to the point where the thresholds crosses 6 volt. Actually, let's say it's 6.1. So we'll go here. We reach let's say 3 point some epsilon. Right. So our light is still on at that point. But look at what happens. In the comparator, we're at 6.1 here. So 6.1 is greater than 6, right? So this is becoming true. All right, so here it turns on. So on means, oops, reset. Okay, reset means we reset to 0, right? We reset to low level. So Q becomes low, becomes 0. Right? So, oh, okay, so the voltage on the output, which I had in green here, so I should have written this as output. That's my output signal. Actually, I need another color. All right, okay, we're gonna put it in dark blue. Okay, so it's gonna be dark blue, is gonna be the output. The output goes back to 0. Boom. Right? Because, okay, we reset. I mean, the threshold is now, I mean, the threshold is just went above 6, it just went above 6 volt. We were at 6 point some epsilon, right? And okay, so, and we reset. So okay, so this is the output is now at 0 because we reset. So Q is 0. Okay. Now non-Q is at 9 volt. Oh, but look at what happens. 9 volt. Okay, now it can flow, right? The current can actually flow here. So it's flowing. It's flowing through this transistor. So if it's flowing through this transistor, well, that transistor is actually on. So discharge actually has just been switched on. So discharge is now going to ground. So before discharge was going to nowhere, but now discharge is going to ground. So the 9 volt the current can actually flow through the 1K resistor and go to the ground. So it's actually dissipating a tiny bit of current through this first transistor. Okay, that's not interesting. What is interesting though is that the current can also go from the capacitor. Now it can flow like this. So before it was flowing in that direction, it was going south, I guess. I mean, it was going this way. So that's capacitor charging. So I'm gonna write charging. All right, so we're charging. But now the capacitor can discharge, right? Again, it can discharge because the discharge 7 is now connected to ground by the virtue of the reset being set to 0, being set on, meaning that the Q is at 0 and then the Q bar, the non-Q, is at 9 volt. Okay, so we're discharging. So the current goes like this from the battery, but it's also going from the capacitor through the discharge while he's discharging. So okay, so this is so in purple I have my capacitor charge. It's discharging. Okay, cool. So slowly, I mean actually very fast, because it can, the 555 timer can go all the way to a megahertz depending on this. It's flashing, I don't know, maybe 10 times a second on my circuit, so it's flashing very rapidly. Okay, so this is discharging, so not so slowly. And look at what happens. When we reach 3, okay, we reach 3 at some point. When we reach 3, well, this becomes, we go below, as soon as we go below 3, let's say maybe 2.9, at 2.9, well, this is lower than this. So in other words, what's coming to the trigger is actually lower than the reference voltage. So this goes on, it sets the latch. It sets the latch, and let's think about this. It sets the latch. Okay, Q becomes on, turns on Q. So we have 9 volt flowing here. So we have 9 volt on the output. So the output was at 0. So boom, suddenly it goes vertical all the way to 9. All right, so now we're at 9. So we went from 0 to 9. Okay, cool. And then we're in the we're in the next cycle. So what happens is our capacitor, again, by the virtue of the non-Q being at 0, the discharge stops, can no longer discharge. So in fact, the current can only charge the capacitor. It can no longer go to ground. So it cannot do this. It cannot flow from the capacitor to ground and flow from the battery through the first resistor to ground. So now it actually can only go this way, and it charges the capacitor again. Okay, so it charges the capacitor, and then we go back slowly to 6.1, and I've just explained what happens. So as soon as we reach 6.1, this becomes true. So the reset goes on, Q goes to 0, non-Q gets to 9. Alright, so this is turning on the discharge, so it starts discharging. As soon as it's, and by the way, it starts discharging, and again, Q is at 0. So if Q is at 0, boom, we're back to 0 on the output. So again, my output is in blue. Okay, so we're gonna go 9 volt to 0, to 9 volt to 0, back to 9 volt, while the capacitor oscillates. So the current on at this side, so the current right there, I'm gonna call it A. So that's the current, that's the voltage in A. So the voltage in A oscillates between 3 volt and 6 volt and 3 volt and 6 volt, while the output, and it does so slowly, right? I mean, slowly as in it's not instantaneous. It takes some time to charge, takes some time to discharge. The time it takes to charge and discharge is determined by the size of the capacitor, obviously. The larger the capacitor, the longer the time it takes to charge, but also those two resistors. So in fact, I probably should write this like this. This is the duty cycle, right? So this determines the duty cycle. So those two guys, if you compute if you choose the values properly, you can actually decide how long each peak and each zero period look like. So if you're looking at the times, let's call it T1, T2, T3. T1, T2, T3 are determined by this resistor. I'm gonna call it R1, R2, and capacitor. I'm gonna call it C. So there's a formula. Let's call it F, and you input R1, R2, and C, and it's gonna decide how long, how much time you have between T1 and T3. This formula is in the data sheet, so I would recommend you go look at the data sheet that I've linked it below in the video. Okay, so this is how it works. So the whole reason to build this circuit, instead of buying a 555 timer integrated circuit, there are dime a dozen, by the way. I mean, it's actually much cheaper than the circuit. Is that you can actually go and put your oscilloscope on any one of those wires. So in fact, you can actually go look at the voltages anywhere inside the capacitor. There are some values that are known. Obviously, the 3 volt, 6 volt. So this is known. Even you don't need to open a 555, and even though you don't have access, I mean, if the components have really good quality, if they are 5K within, like, and the error is less than 5%, the tolerances generally on the components you buy are generally 5%, but on these internal components probably less than 1%. So those guys are known with very good accuracy. So you don't need to open the 555 timer for those. However, everything else, I mean, it's a black box, right? IC is a black box. So in fact, the fact that you recreated the IC, the integrated circuit, is actually makes it possible to actually go and probe the inside of the 555 timer. So you can actually, with a simple voltmeter, you could actually look at what the values are on some of the ones that don't change their value, right? There are 3 modes on the 555 timer. This is the only one that we're going to look at today. It's the astable mode. But if you understand this circuit, which honestly I did not understand as well until I actually looked at the board. Once you look at the board, it becomes absolutely obvious what's happening. It's really crystal clear, and you can, if you build this board and you do this circuit and you look at this diagram, you cannot. It's very easy. You cannot forget it. You will know it forever. And the formula is in the data sheet, so you can actually go there, download it from Texas Instruments website. It's a PDF, so it's a PDF, and I've linked that PDF down. So if you want to change the values, if you change the values, it will change the frequency at which the diode is actually blinking. So the blinking frequency again is determined by this guy here, and you can change those components. You can actually, I would actually recommend to put a variable resistor here, because you can actually, if you put a variable resistor, you can go from blinking very fast to blinking very slowly. So that's one way to do that. Actually, or even better, change the R1. The R2 is going to change the distance between those. It's going to determine where that line falls between that line and that line. So that's what the R2 decides, and the R1 plus R2 is going to decide along. That's the R1 plus R2 is going to decide along the whole duty cycle is. Now, if R2 is very small, if R2 is near 0, what's going to happen is going to be that this line is going to fall exactly in the middle. The closer, the larger the R1, the smaller the R2, the closer this line is going to be from 0. So from the middle. From the middle between these two lines, between this line and that line. So it's very easy to change. So in the circuit, I made it exactly like they are recommending. I put the one. I went to my box and I did 100K, and that's what you saw on the video, in the first video and second video. I'm using those values. However, I would recommend 100K and 1K. If you do 100K and 1K, this one is 1%. This would be 1% of R1. And if it's 1% of R1, the time that the diode spends off is going to be almost equal to the time that it spends on. So of course this is off, diode off, and that's the diode on, LED on, light emitting diode, right? LED, there you go. So that's the diagram. You can pause it and you can go and look at it and then replicate it with a small board, with a breadboard. I would recommend doing it. I mean, that's one way of making sure your 555 timer actually works. So and then with that, I'm gonna wish you good luck, and thank you for watching this video, and I hope to see you in the next one. Bye.